Good evening, everyone. We are in the week 3 problem solving session of the NPTEL course, Control and Tuning Methods in Switch Mode Power Converters. And week 3 is about fixed frequency control methods. I am Teja, Golla, a 5th year research scholar working under Dr. Santana Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Is my screen visible?
Yes, it's visible.
Yeah, so this week we'll be learning about a few things. First, we'll discuss about the practical voltage source. So before we move into the modulation techniques, let us quickly just go through what is a practical source. So I hope everyone can see my screen.
Yes, we can see.
Okay. So why practical voltage source is important, and how is it different from an ideal voltage source? So first let us discuss about ideal voltage source. So here we have an ideal voltage source connected to some load. So what is an ideal voltage source? Ideal voltage source, if we draw the IV characteristics, if we are drawing the voltage versus current waveform, so no matter how much current we are drawing from the source, the voltage will remain constant. So if I am connected a load such that it is drawing 1 ampere, the input voltage will remain Vs. If I'm drawing 10 amperes, input voltage will remain same. And if I'm drawing 100 amperes, input voltage will still remain the same. So that's why if we are drawing the voltage versus current, no matter what is the current, the voltage will remain constant. So the graph will be V equals to Vs. So this is an ideal voltage source. So here we can say that the voltage remains constant in respect of the load current. With respect to of the load current. So that's why the equation, if we write, the equation is like V equals to what is the voltage source Vs. So it's a line which is parallel to the I-axis. So it is here it is parallel to x-axis because current is on the x-axis. But every time this will not happen in this way, because in the case of practical voltage source, there is some parasitic resistance. So the source that is inside this box, maybe I'll change the color. So this is the source. So here in this case, this is the source. So the source internally as an ideal voltage source plus some parasitic resistance. So if we consider this case, so we have ideal voltage source plus parasitic resistance. Ideal voltage source plus parasitic resistance. So in this case, what happens? So the source that is inside the box contains one ideal voltage source, plus it also contains some parasitic resistance. Now, if I want to calculate Vs, uh, can anyone tell me what is the expression of Vs in terms of V in RD as well as Is? What will be the expression?
Vs will be Vn minus Is into Rd.
Yes. So if you calculate the expression, we will get Vs is nothing but V in minus RD into IS. So this is the expression that we are getting. So if you calculate the slope, it will have a negative slope. And as IS increases, so what we are trying to say is, as IS increases, VS will decrease. So there will be parasitic drop across this resistance. So the effective voltage that the load will be seeing will be dependent upon the current that the load is drawing. So if the load is drawing so much current, then what happens? The effective voltage will go down. So that's why this dotted line is the ideal case where there is no drop, ideal case, and this is the non-ideal case. So as you can see, so now it puts a limitation because if we cannot draw infinite amount of current, whereas in the first case, I can draw infinite amount of current and then the voltage source value will remain the same. However, in practical scenario, that is not the case. So it has some parasitic resistance. Because of this, what will happen? Because of this, the voltage will drop as the current increases. So we will not have the same voltage as this Vin at the end of this source. So there will be a drop across this resistance. So is this clear?
Yes, clear.
So now if you see this parasitic resistance is not frequency dependent. Sorry, not frequency. Yes, not frequency dependent. It is basically frequency independent. But if we consider the overall model of all the parasitics, it has frequency dependent parasitics. So if we have to highlight, this is frequency independent. Frequency independent. So we are going step by step. First, we have gone ideal, then we have done non-ideal, which consists of ideal voltage source plus parasitic resistance, which is frequency independent. Now we have ideal voltage source, ideal voltage source plus frequency dependent parasitic. So now let us see. This is the effective volt. Now this is the effective voltage that the load will see. So we not only have a parasitic resistance, but we also have parasitic inductance. So this is the parasitic inductance. So similarly, we have capacitance. It will also have some parasitic resistance. So now what happens is, in this case, say the load current is fixed, right? And then if the load current is fixed, then the voltage is fixed. And say we are having a load current that is in a square waveform. So let us assume the load current is changing like this, right? So this is my I naught. And then how will my V naught will change? So I think let me draw this. So if I'm calling this case 1, and if I'm calling this case 2, and if I'm calling this case 3, and what I'm trying is, I'm trying to consider one scenario where we have something like this. So I am drawing my I naught in this way. So I have to add one more section. So basically we are drawing I naught in this particular way. So I naught is like this. Okay. So it is changing in this way. Now, how the voltage will look like in all these three cases. So here we have case 1, and what is my VS? VS is the effective voltage that we are seeing. VS. Case 2, what will be my VS? Case 3, what will be my VS? So can anyone tell me how it will look like in the first case? What will be the Vs?
A straight line,
Straight
irrespective, it
line.
won't
Yeah, very
change
good.
with I naught. Yeah.
Yes, very good. So it will be like a straight line. The value can be anything. So here I have considered some value. Maybe let us align with the grid. So it will be nice. So in the second case, anyone how it will look like?
Reducing slope when I naught is not non-zero, and it will be straight line when the I naught is 0.
Okay. So you are almost correct. But if I naught is fixed, then this voltage is also fixed, but it will be smaller than this. Here it is looking like this because it's a function of I naught. But say our I naught is fixed. Say I have fixed this value of I naught. Sorry. Say I have fixed this I naught. Then my Vs is also fixed, although it is smaller than that. So whenever there is higher I naught, then the Vs will be a little bit smaller. Whenever it is 0, then it will be the actual voltage. Else, again, it will be smaller. Is this clear? Because once we fix I naught, voltage will be fixed, but it will be lesser than what it is supposed to be. So whenever I naught is like this, then it will have this voltage. Whenever it is like this, then it will have this voltage. So is this clear?
Yes, it's clear.
But what happens? So now here there is no frequency dependent. So again, we are not having any dynamics. But if we consider frequency dependent parasitic, then what order system is this? Anyone? First order, second
Second,
order, third order. Okay, and how are you saying that it is second order?
LS and
Yes,
1 by SC. So if we did, then it will become S square.
yes. So we need to see what are the energy storing elements. We have one inductor, so one capacitor. So there are two elements, and both will contribute to two different terms. So we'll have two S term. So if we write in the what do you say in Laplace domain, we'll have SL as well as 1 by SC. So we'll have S square. So because it is having two such elements, we'll have second order. However, if we have two inductors in series, then we can combine it as a single inductor. That in that case, it will be first order, but here it will be second order. So now not only the value will be smaller, but during the transition, there will be an effect. So what I'm trying to say is, so this is how it is in the above case. But now what happens is it will have a second order effect. So there will be oscillations. And again, here also there will be oscillations. So now not only the value is changing, but also it will have a different frequency components. So it will have some harmonics. So in this case, there will be harmonics. And it may lead to EMI. Say my load current is swinging or changing between two values at a very high frequency, then it will have very high frequency and that will cause EMI problems. So whenever we are making a product, there will be requirement, EMI requirement, and it should be within that requirement. Else it will, because this is the power supply, right? So you cannot have very high frequency pulsating current that can be drawn from the power supply. Because of this, say current is changing, and we know VL is what? VL is L into di by dt. Say if my current is changing step, then the voltage across the inductance will have a impulse, right? There will be an impulse, or we can say there will be a spike. So this will cause EMI problem. So whenever there is inductance, you cannot change the current in a step fashion. Then there will be derivative of inductance in the voltage across the inductance expression. So it will cause impulse or spike. So this will lead to EMI problems. And that's why we have to be very careful whenever there is frequency dependent parasitic. Is this clear?
Yes,
Like
clear.
the three differences between these three cases. So this is the oral parasitic model of the practical voltage source, which consists of all the parasitics as well as it consists of the frequency dependent parasitic, both this as well as that. Okay. So now let us quickly write the expression of Vs. So Vs will be nothing but Rs plus 1 by SCS by Rs plus 1 by SCS plus RD plus SLS everything into Vn. Agree? Everyone?
Yes.
So now if I multiply by SCS on the numerator as well as the denominator, then I'll be getting this final expression, which is Vs is equals to S into Rs Cs plus 1 by S squared Ls Cs plus SCS into RT plus Rs plus 1 whole into Vn. Agree? So when there is no load, so I am just calculating uh, as if load is not there. So I have disconnected the load, else there will be loading input. So basically, I have disconnected the load, and then I am calculating the uh, voltage across this point. Say when there is no load. If there is load, then we cannot directly do this because there is current flowing in this direction also. Clear? So now from this we can say that it is the second order function. Is this clear how we are getting this expression?
Yes.
Okay. So if you have any queries, you can ask, else we'll quickly solve one problem. So I hope there are no questions. If you have any questions, you can stop me. Okay, so I guess no. Then we can move to our next part, which is implementing this circuit where ILF is the input and VT is the output. So sometimes it might be given like the question will have a complicated circuit, but basically in this question we are not asking the entire implementation of the circuit. If you see what is given, ILF is the input, so ILF is the input, and then VT is the output. So basically ILF is the input, and then VT is the output means only this branch. So basically the question is asked about this branch, right? Not the entire circuit. So my input is ILF and my output is VT. So I need to write an expression in terms of ILF so that I can write it in terms of MATLAB implementation. MATLAB implementation means we'll use gain blocks as well as integrated blocks. So basically we are using gain blocks as well as integrated blocks. Is that clear?
Yes.
Did you understand the question? Everyone?
Yes, understood the question.
Okay. So now first we need to calculate the current in the capacitor. Say current in the capacitor, I am calling it as IC or say ICF. Now, can anyone tell me VT relation as well as ICF relationship between VT as well as ICF?
VT equals to ICF into RF2
Okay.
plus
VT is equals to ICF into RF2
plus
plus
VCF.
VCF. Yes. So now we got one relationship. where ICF is our input and VT is our output. But VCF is something we do not know, and it has to be as a function of ICF. So what is the relationship between VCF as well as ICF?
1 by CF integral.
Yes. So VCF is nothing but 1 by SC into ICF, right? So we'll have VT is equals to ICF into RF2 plus VCF is what? 1 by SC into ICF, right? Agree?
Yes.
So now I can simplify this and I can write it something like this. VT is nothing but ICF into RF2, which is a gain block. Then I have one integrator block, and then again I have one gain block. So this is the relation. But I also don't know ICF. And what is ICF now? What is the expression for ICF? What is the expression for ICF? Because ICF, I want in terms of ILF, everything in terms of ILF. So what is the relation between ICF and ILF?
ILF equals to ICF, right?
Just that or something else is also there?
Oh, plus
IT is
IT.
also,
Okay.
yes, yes. So
ILF equals to ICF plus IT.
yes. So if we say, then we'll have something like this. So ICF is nothing but ILF minus IT. Right? Clear for everyone how we are getting this?
Yes.
Okay.
Yes.
So now we need to represent this using the MATLAB blocks that we know. So gain blocks, integrator blocks, as well as summer. So summer block is also there. So this will be at this will be on the left hand side and this will be on the rightmost side. So whenever we are implementing in the MATLAB, so either we can start from the left side. So left side there will be input, right side there will be output, or right side there will be input, left side there will be output. But usually when we draw, it will be good if we draw from left hand side. So on the left hand side we have the input, which is ILF. So I'll use a summer block. So this will be plus and this will be minus, and this will be ILF and this will be IB. So now what is the output? So what is the output of the summer block?
ICP.
ICF. Sorry.
ICF. Yeah. ICF.
ICF. So
ICF.
this is ICF. Okay. So now from ICF, how can we get VT? How to implement this?
One by SCF and
One gain.
RF2.
Okay, one at a time. Who is talking? Maybe Arun. Arun first, then Prasad.
We have to pass one ICF through 1 by SCF
Okay.
and pass the same ICF through a gain block of
Okay.
RF2. Then add both.
Yes. Prasad, do you agree to what Arun has said?
Yes, yes.
Yes. So now ICF is the input and there are two blocks that needs to be summed. So ICF will be divided into two blocks. In the first block, we have gain. So I am using a different color for gain. So say we can say RF2. So I want RF2 here. Similarly, on the this side, we have 1 by C. And then in the below side, we have another block which is integrated. So I'm using a different color for integrated. Now these needs to be summed. The output is yield. And this is plus, this is also plus. So is this clear for everyone? How we got this?
Yes.
Yes.
Okay. So now the implementation of this is what we have done. Similarly, you can also implement this, right? If I'm asking in terms of VT, VS, you can also do this, right? For series resistance plus DCR, like sorry, inductance. Will you be able to do, or should I solve? This part, say VT is given and VS is given, and we need to get ILF current. Clear, or should I also show that?
Just one clarification here. That
Yes,
will
yes.
come as LS, SL that will come, right? So that will be
Yes,
as a
SL.
product. But
Yes.
S block, that is not available. Like we have to express in the form 1 by S only.
Yes, yes, very good. So yeah, that's a very good point. Maybe I'll just tell. So he's right. In the case of practical implementation or MATLAB, 1 by S is available because this is proper transfer function. And this is very important. You can be asked in any interview. So this is proper transfer function. Or I can say strictly proper. So strictly proper means the order of the numerator is less than the denominator. So then in that case, it will be strictly proper. But if the order of the numerator as well as denominator is same, then it is proper transfer function. So this is basically strictly proper transfer function because the order of the numerator is 0 and the order of the denominator is 1. If we consider S, this is improper transfer function. And all improper transfer functions are practically not implementable because with frequency, the gain will keep on increasing, right? And it will become infinite. And practically that is impossible to implement. Similarly, in the case of MATLAB, you will not get S block. So for capacitor, you have 1 by S block, but what happens to the inductance? So that we will see. So if we write the expression Vs minus Vt is equal to voltage across this RF1 plus LF, right? So Vs minus Vt is equals to current is ILF into RF plus voltage across the inductance, which is VLF. So VLF is nothing but SLF into ILF, right? So whenever we have capacitor, things will be very simple because it is in 1 bias. But whenever there is inductor, then things will become difficult. So how are we going to implement this? So this is basically VLF, right? So this is basically VLF. So let us only consider VLF. So we'll have VLF is equal to SLF into ILF. So now I can calculate ILF from VLF, which is 1 by S into 1 by LF into VLF, right? Is this
Yes.
clear? So now I can get, if I know VLF, then I can get ILF. And if I know ILF, then I can get this first expression. And then I can add these two to get Vs minus Vt. So like one is dependent on another, so there will be a loop. So let us start from this. So first let us calculate VLF. What is VLF? VLF is nothing but Vs minus Vt minus ILF into RF, right? Everyone agree? What is VLF from here? So if I write VLF, I can write VLF is equal to Vs minus Vt minus ILF into RF, right?
Yeah.
So consider this as expression 1, consider this as expression 2. Now we need to implement these two expressions using MATLAB. And once we will implement, then you will know how the implementation is done, because this is little bit tricky because there are independent terms in both sides. So first let us start with this equation 1, and then we'll move to equation 2. So equation 1, I am using a summer block, and then we have three inputs, right? So input 1, input 2, we have input 1 here, input 2 here, and input 3 here. So input 1 is plus, others are minus, right? So so what are the plus term and what are the minus terms? Anyone? What are plus terms and what are minus terms? VS is plus,
VS
very
is
good.
plus VT and
Okay. And then
IRF is
ILF, RF is negative. But the question is, how do we know ILF? So we'll get back there. So what is the output of this summer block? Anyone? What is the output of this? VLF. Very good. So the output is VLF. Now we have VLF. So now I know VLF. Can I get ILF from this?
Yes,
Yes.
put it through an integrator and
Yes.
through a
Gain. So first
gain
I'm
block
putting a
1 by
gain, and I am calling the gain as 1 by LF. And now the gain block is going to integrator. The output of the integrator is ILF. Okay. So here I have ILF output. Here I need ILF into RF. So how can I connect these two? Anyone?
gain.
Gain. Yeah, very good.
No,
So
gain of
yeah.
basically,
RF and put it
yes. So basically, I am connecting a block RF 1. So RF 1, and then I am connected. Okay, so that's why there is a loop here. Whereas in the case of capacitance, it is straightforward. So you will not have that confusion. So whenever there is S term, you have to convert it into 1 by S. So VLF is in terms of S. So I cannot get VLF from ILF because VLF equal to S into something. But I can get vice versa. I can get ILF from VLF because it has 1 by S. So I first have to calculate ILF from VLF. So now I have checked what is VLF. So I got VLF. Then from VLF, I got ILF. So then whatever terms are dependent on ILF, I have supplied. So now this ILF can go here. So basically, we can combine this and we can combine that. So if I take this and if I keep it here, so basically what happens is this will complete. So now from VS and VT, we got ILF, and from ILF and IT, we got again VT, right? So basically, ILF and ILF is combined, and VT and VT are combined. So what happens in this entire circuit? We have one input which is VS and we have one output which is VT, and everything is part of the circuit. So this will become our overall entire circuit. Is this clear? So basically we have broken the circuit into two parts. One is this part, one is this part. We have implemented both and then we have combined both. Is this clear? If you have any doubts, you can ask.
The IR is left without connecting anything.
Sorry.
IR is left, sir, without connecting.
Which one? IR.
Yeah.
Which IR? This one.
Yeah.
Sorry, this is not IR, this is IT. So this is also like input. So when we are saying input, which are not in our hands. So in this entire circuit, VS is given input, and there is some load connected which has some voltage VT and which has some IT. So depending upon the current IT drawn, VT will be decided, right? So IT should also be given, then my output will be VT. So basically IT is also input, VS is also input, and VT is the output. Yeah, you are right. Thanks for pointing it out. So these two are inputs, and this is the output. Output, OP, input, IP. So this is input, and this is also input. So these two are inputs because IT has to be given. So for a given load, as we have discussed here, so if the load current is given, then only we can calculate VS. So eventually VS is the output, but for that we need to know two information. One is what is V in and what is the current that we are drawing. So what is my ideal voltage source VS value as well as how much current that I am drawing. If I'm given these two inputs, then this is my overall output, which has all the parasitic, both frequency dependent as well as frequency independent. Now is this clear? Everyone? If you have any doubts, you can ask. So this completes our topic on the this dependent as well as independent voltage sources. Now we'll move on to what are the control objectives. So the meeting will end within a minute. So once it ends, let us come back and continue our discussion, because the part of this course is the control, right? Control objectives. So we also need to know what are the types of objectives for control. So basically, when we say types of objectives, they are objectives of the controller or the overall system. So whenever we are designing the control and running the overall system, it has different objectives dependent to multiple things. When we say static objectives, so it will have ripple consideration, like inductor current ripple, output voltage ripple. So we'll have IL as well as remote. So if this meeting ends, kindly join back. And then we also have efficiency, which is like a static at steady state. Basically, static means steady state. So what is the ripple criteria and what is the efficiency? And we can also say how much is the area that things are occupying. So we can also say power density. So we also have power density. And when we come to dynamic objectives, then we are more worried about the performance. So when we say performance, say there is load transient or reference transient. So the basic questions is what are the voltage overshoot? What are the voltage undershoot? Peak current? How much is the peak current? Also, main important thing is the settling time. How fast is the converter settling to the change that is given because of the load transient or reference transient, all these things. And when we come to operating requirements, one thing that we have discussed about is the EMI. So whether EMI is met or not, and then what is the power up sequence. So say you have a laptop or you have a phone. Once we turn on the laptop or once we turn on the phone, so say laptop is a better example. So once we turn on the laptop, you know that it goes through certain process before we get the home screen, right? Before the laptop gets on, where we need to enter the password. So it has some sequence. So it will turn on one by one. So when we press the button, there are certain sequence they follow. So first they'll turn on this, then they'll turn on that. and then they'll run the program. Then we'll get the home screen where we'll enter the password. So there is some sequence. So that is called power up sequence. Also, there is something called startup, which is also like more or less correlated with this. Say once our phone is in sleep mode, and then brightness is off and nothing is displayed on the phone. The moment we'll click on the power button, so the display will be on, right? So previously the display is off, now the display is on. So now once we click that button, it has to start the circuit, also it has to display. And then that process, there are some rules and guidelines that we need to follow when we are doing that, because now there is no load on the screen as such. So it is operating at no load condition. Once we click that button, now the screen has to turn on and it is going to some loaded condition. So when it is going from no load to some loaded condition, there should be some sequence, like a startup sequence, so that there will be control on the current as well as the voltage, which will come under the startup logic. So these all will come under the operating requirements. Now, once we come to fault management as well as protection. So we have many protections like under voltage lockout, and then over current protection, then over voltage protection, then over temperature protection. So I'm not sure how many of you might have used keypad phones. So if you see keypad phones where we could take out the battery, so the battery used to have three terminals. You used to see three gold color terminals in the battery if you had removed the battery. So there are three terminals on the battery. So if I'm considering this as battery, the old battery, old phone. So then there used to be gold color three pins. One, two, three, which used to get in contact. So these gold color pins consists of three terminals. One is the plus VDD, and one is the ground, which is minus, and one is for temperature. So whenever you are charging a battery or anything, it also will get heated up, right? So there should be also a feedback of the temperature. So the temperature will not be beyond certain limit, else the battery will get damaged. So there needs to be control over temperature. Also nowadays, if you see, there are fast charging phones where the current can be high as well as the wattage can be high. So there should be also control over the current. Current cannot be so much high so that it will damage the components. So there should be some control over the current as well as the voltage, of course, because the battery has certain voltage limit. If the voltage exceeds, then all the components that are connected to the battery will get damaged. So they need to have minimum voltage again. So if the voltage of the battery goes below certain level, then the performance of the phone will become much lesser and the performance will go down. When this happens, when the phone percentage comes down, then it will not work as fast as it had worked when the battery is high. So it is again dependent on the voltage of the battery. And if the voltage is below par, then it is the minimum is required, then it comes under voltage lockout. So there is something called under voltage lockout where the devices will get shut down once the voltage is less than this minimum voltage. So fault management protection is very, very important for protecting the device, laptop, phone, and everything, where you need to have over current, over voltage, over temperature, as well as under voltage protection, so that the device will not get damaged. And this is very, very important with the way the technology is growing, and everything should have all these objectives. So mobile phone, maybe it could be mobile phone, or maybe it could be laptop, which has controllers, everything inside. There are these four main objectives, and each of them are equally important when we are considering a product. So in the case of product, all these should be met and all these should be maintained for the safety of the user as well as the device, and to meet the requirement of the user, laptop, everything. So is this clear? What are the key objectives of controller and how it is important, and what do they include?
Yes, clear.
Yes. So now, if we see the overall control objective, so we have seen that these are the four objectives that we need to keep in mind when we are designing the controller. So considering these objectives are fulfilled and we have designed the controller, and here sir has shown a buck converter, but it could be of any converter, right? So this converter can be anything. So this is our plant, which is a converter in this case. So this is a plant, which could be any converter. Here it is a buck converter. So whenever we are designing a controller, we need to have some inputs and it will have some output. So always when we are designing a converter, the output of the controller, the entire control loop is always a gate signal, because the converter is run by switches and at the end we are basically controlling the switches, right? So it's always the gate pulses of the switches. And modulation techniques are what? Modulation techniques are different type of techniques, whether it could be leading edge modulation or trailing edge modulation, like we have discussed in the last week. There are different type of techniques to generate the gate pulses. So there are different techniques to generate gate pulses from the control input. So control input we call, which is the controller output. So now this is the controller. So this is our controller, feedback and feedback control methods. So sir has discussed in his lecture that both feedback and feed forward are needed in order to have a like a very improved performance, very fast response. So we will be using both feedback as well as feed forward, and sir has shown some results where the response has been significantly improved using the feed forward control methods. So when we are designing the controller, it will again need certain signals. Like if you see here, it needs input voltage. When there is input voltage feed forward, and V reference is the reference voltage at which we are trying to regulate the output. And of course, it needs the output voltage as well as load current. So when we say feed forward, there are different type of feed forward. One is the V input or input voltage feed forward, and another one is the load current feed forward. So both of them are advantages in two different things. Input voltage feed forward will improve the audio susceptibility. I0 feed forward will improve the output impedance. So the details of which and how to design, again, we'll be discussing in the upcoming weeks. This week is just to have an overall idea of what needs to be kept in mind while designing the controller. So the controller will consist of both feedback as well as feed forward to have very high like bandwidth or much better transient response, and it can include V in feed forward, I0 feed forward, or both or none, depending upon the requirement. But this is the overall idea of the controller. This is the controller block. And what is the input to the controller? The signals that it needs, like this input voltage, output current, also mainly the output voltage. So the first question is, why can't we directly feed V0 into the controller? So that is one thing. What happens if we directly give V0 to the controller? So the converter, as I have said, plant can be of any converter. Plant can be of low voltage converter or very high voltage converter. So whenever we are designing a controller, basically what in which domain the controller is in? Controller is in digital domain, right? So it needs digital data. So there has to be one ADC. So there has to be one ADC which converts the analog data to digital, right? So now ADC will have voltage limit, right? Like what is the voltage limit of the input? So nowadays, you can say microcontrollers that people are using, they'll have 0 volt to 3.3 volt. So my input should be 0 volt to 3.3 volt. Say, but my output of the converter is 50 volt or 100 volt. How can I feed it? So I have to step it down from 100 volt or 50 volt to 0 to 3.3. So this is called signal processing. We are processing the signal and then we are passing through ADC and then we are getting the digital data, and then that digital data is fed back to this controller. So that's why this is very much needed. So this will process the signals, whether it could be stepping down from higher voltage or it could be converting from analog to digital, so that the signal can be fed back to the controller, or it can be of anything, like it can be filtering also. So it can include many things. So few of them are, one is stepping down, another could be filtering, so that noise is filtered. The other thing is ADC conversion, so that the data can be converted into digital. So this is the overall architecture. So in this slide, we have discussed about what are the objectives of controller, the four main objectives, and what does this individual objective mean. And then we have seen what is the overall structure of the controller, and what are these individual blocks are for, and what are their working principles, and why they are needed, and what is the important thing that needs to be considered while designing the controller. So is this clear, or if you have any doubts, you can ask. Any doubts?
No.
Okay. So now, if we don't have any doubts, then I'll move further to the next slide, where we will be discussing about one thing, which is the input voltage feed forward that we have highlighted over here. So let us move to input voltage feed forward. So I'll give a brief intro about input voltage feed forward. Before we solve a problem on this. So in the last week, we have studied about the trailing edge modulation, where we have a ramp signal. And then we have a control voltage that is being compared. So this is my Vcon, and this is my ramp voltage with the maximum value Vm. So can anyone tell me, if I calculate the duty ratio from this, what will be my voltage? Sorry, what will be the duty ratio expression in terms of Vcon as well as Vm? Basically, this is my duty ratio, right?
Vcon by Vm.
Yes. So it will be Vcon by Vm. Very good. So this is my duty ratio. And if I'm calculating duty ratio is Vcon by Vm. Okay. So now if I calculate the output voltage V0, then I'll have V0 is nothing but D into V in, right? But there is a dependency of V0 on V in. Say I don't want any dependency of V0 on V in, because say input is changing. In the converter, input is not in our hands, right? Input can slightly fluctuate, but the output has to be regulated. But if I don't want my V0 to be directly dependent on V, how can we introduce some feed forward? Basically, in this here we are discussing about feed forward. Can introduce some feed forward technique so that the dependency will be removed. So, sir has considered one example. So V0, if we replace D, which is V control voltage by Vm into V input voltage. So control voltage is not in our hands, it is coming from controller. But the sawtooth that we are comparing, this is in our hands. So what if the voltage, peak voltage of this sawtooth Vm is a function of Vm? Say Vm is nothing but some feed forward gain into Vm. Now Vin will get cancelled. And then if you calculate, we'll get V0 is nothing but Vcon by K feed forward. So now in this case, say control voltage is fixed. Say Vcon is fixed. Vcon is fixed to some value. And K feed forward is a gain, which is also fixed. So now even if I change my input value, say from 5 volt to 10 volt or 15 volt to 20 volt, my output will still be independent of input voltage because my ramp height is adjusted based on the change in the input so that my output voltage is independent of the input voltage. So basically here we have introduced one feed forward. So this is the feed forward that has been introduced. Feed forward technique. And here to be precise, it is input voltage feed forward. So that my output voltage is independent of Vin once the control voltage is fixed and the gain is fixed. No matter how much change the input sees, the output is independent of input voltage. So is this part clear? How input voltage helps us to remove the dependency term of V0 on Vin?
Yes, but will this technique work on leading edge also? Like if we interchange the S and R, like if we give
Yes,
to the R.
yes, you are very much right. It will work on the leading edge also because we have seen even in the leading edge duty ratio is Vcon by Vm. So it will work on both leading edge as well as trailing edge. Here for simplicity, we have considered trailing edge, but it will be equally applicable to leading edge as well as trailing edge both.
Okay, thank you.
Okay, so now if we solve quick problem, so let us consider a buck converter under voltage mode control with input voltage feed forward, and KFF is given 0.2, V0 is given 2 volt. So what is the value of control voltage? So what will be the value of control voltage, anyone?
0.4.
0.4. So very good. So it's a simple question. Vcon is nothing but V0 into K feed forward. So from this, I can get Vcon equal to 0.4 volt. Okay. So now I'll ask a few more questions. Say input voltage is not given. So I have another question. My input voltage is 10 volt. And then my Vcon, what will be the value of Vcon? What will be the value of duty ratio? And the second question, Vin is 20 volt. What will be the value of Vcon? And what will be the value of duty ratio? So anyone can solve this question. So in the now I have asked few more questions. Say my input voltage is 10 volt. What will be the value of Vcon as well as what will be the value of duty ratio? And in the second case, I have Vin to be 20 volt. So what will be the value of Vcon as well as what will be the value of duty ratio? So what will be the value of Vcon in the first case? Anyone?
0.4. only.
0.4, yeah, very good. So if you see our Vcon is independent of input voltage, so we can directly say, so I am solving the first case here. So my Vcon is 0.4 volt. So how to calculate duty ratio now?
V0 by Vn.
V0 by V, yes. So we can either do V0 by V, or you can also see D is Vcon by Vm, right? And Vm is K feed forward into V. So you can do any of those things. So if we go by this method and then check whether V0 is dV, so we can calculate D as Vcon by KFF into V input, right? So my duty ratio D is Vcon by KFF into V in. So what is the value?
0.2.
0.2. So now if I back calculate V naught, which is dV, so I'll get V naught is 0.2 into 10. So my V naught is at 2. So now let us solve for the part B. So for part B, what is the value of V con?
Same 0.4.
Same. Yeah, same. So it will be same because it is independent of input voltage. Now what will be the duty ratio? V con by KFF into input voltage. Right? So what is duty ratio now?
0.1.
0.1. So if I calculate V naught again, V naught is 0.1 into 20, which is again 2 volt. So if you see, no matter what is my input voltage, if my control Vcon is fixed and if I have this feed forward mechanism, the disturbance in this independent input voltage will be taken care by this logic so that my output is regulated at what it is supposed to do. Because we have basically removed the input voltage dependency. So we can say that V naught is independent of input voltage. Is this clear? How we are getting this independency?
Yes.
Okay, so here we have considered a buck converter, which is easy and straightforward. Now let us see whether the same can be applicable for a different converter. So here I have given one question based on boost converter. So let me read it out for you. If a boost converter operates under voltage mode control with input voltage feed forward, what will be the output voltage? Sorry, will the output voltage remain independent of the input voltage? So if not, then what will be the relationship between the input and output voltages? So let me ask you the question. Do you think in this case also the output voltage will be independent of the input voltage or whether there will be any dependency?
There will be a dependency.
Okay. What about others?
Yes, because V out is equal to 1 by 1 minus D into V in. It is not
Yes.
linear.
Yes,
Linear
yes,
relation.
yes. Yes, very good. So first, if you see the basic difference between buck and boost, so in the case of buck, if I consider buck, V naught is equals to D into V. In the case of boost, V naught equal to 1 by 1 minus D into V. And for both the cases, we have considered our duty ratio D is equals to V con by KFF into V. So in this scenario, if I substitute this D, V in will get cancelled. So basically here what we are getting, V in is cancelled, right? But if we consider this scenario, V in is not cancelled. So there will be a dependency term of V naught on V in. So how are we going to see like what will be the dependency? Basically, we need to substitute this duty ratio in this expression. So let us substitute it and then see how the V naught is dependent on V in. So V naught is nothing but 1 by 1 minus V con by KFF into V in into V in. Right? So if I substitute or if I simplify it, I'll get KFF into V in square by KFF into V in minus V con. So now you tell me, if the input voltage increases, whether V naught will increase or whether V naught will decrease. If V increases, then what will happen to V naught?
Can't say actually, because it might increase or decrease, right?
Okay, when can it decrease?
No, it will increase only. Okay.
Yes, it will mostly increase. Again, as you said, there can be some region where it can increase or decrease. So one better way is, like if I rewrite this, I can write it as 1 by V in minus V con by KFF into 1 by V in square. So I can write it as 1 by V in minus constant K by V in square. So like let us see whether 1 by V in is always bigger than K by V in square. It has to be, right? Because this is a positive. So 1 by V in has to be always greater than K by V in square. So 1 by V in should be always greater than K by V in square. Then you can get that V in should be greater than K. So this is the practically like if the output voltage is positive, then this is the condition that we are getting. Now, another question is, say my V in is increasing. This is increasing. V in square is also increasing. And V in is not in between 0 to 1. So it is above 1. So V in square is much, much higher than V in. So if this is increasing, then this will decrease, but this will decrease more because there is V in square. This will decrease more, right? So basically the denominator is decreasing, but there can be some region where you said that the subtraction between those two can or cannot increase. So assuming the denominator decreases, then the numerator will increase. But we will get better understanding because it's a nonlinear function by plotting. So we can use MATLAB or any online toolbox where we can plot this and then where we can get a better understanding of in which region it is increasing or decreasing, because it may not be always strictly increasing, right? There can be a region where it may change. So it's a nonlinear function, but typically it is increasing. So now you can see that the input voltage feed-forward logic may not be equally applicable for all the converters, but depending upon the converter, we might have to change the logic. So we can achieve what we can achieve our objective. The objective is to remove the dependency between these two, but here there is a nonlinear dependency. So here there will be a nonlinear function which you need to implement so that the dependency will be removed. But it is not so straightforward. Implementation might be difficult, but the overall objective of this question is to highlight that the input voltage feed forward may not be as easy as buck converter when it comes to other converters, and it may not also work in the way that we think. So depending upon the converter, depending upon the logic, the complexity might increases, and then the practical implementation might be challenging. So this is why I wanted to discuss this. So is this clear,
Yes.
everyone? Any questions until this point?
Teja, was one off-topic question.
Okay.
Like in voltage control mode, if I change the load current,
Yes.
will that have an impact in the in the output voltage? Like, will that also have an impact? Like, if I change the load current in a voltage control mode?
Okay. Yes. Yes. So it will have an impact, but the controller will take action so that the output voltage will come back. So say my load current is changed from one value to another value, say I not one to I not two. So then my inductor current can change. Say my inductor current is like this. Then then it might be undergoing some kind of transient, and then it will settle at the new current because the again this I am considering for a buck converter because it is simple to understand. So this is my I inductor current. Initially it is supplying this load current and now it has changed. Now my output voltage, which also has some ripple, it will see some undershoot and then again it will come back. So this is my output voltage. So now what will be the controller's objective is whenever there is a disturbance in terms of load or it can be any disturbance, it has to make sure that the disturbance is rejected. But in this case, the load is demanding more current. So controllers work or the controller's duty will be to make sure that this load current is met. But output voltage should remain same. So it will again come back. So now when we are designing, what will be worried about is how much is the settling time and how much is the undershoot. So a very good controller will have minimal undershoot as well as minimal settling time. So this we'll be discussing in detail when it comes to the controller design. We'll use two different type of model. One is small signal, one is large signal, and we'll see why large signal can improve the performance with minimal undershoot as well as settling time. So yes, in this is equally applicable for both voltage mode control as well as current mode control, where there is a disturbance in the current, the controller will act and then the response will be changed so that V0 will see an undershoot as well as inductor will undergo some dynamics. But the difference between the voltage mode and current mode control is the shape of the or the dynamics might be different. In the case of buck converter for voltage mode control, so again we are considering a buck converter. If we see voltage mode control, and then if we see current mode control, voltage mode control will exhibit a dynamics of a second order, and this will exhibit the dynamics of a first order. And how we know this? Again, this will be discussed in the upcoming weeks. When we model the converter, we'll see that the voltage mode control of a buck converter is of second order. So the response will be of a second order, whereas the current mode control of buck converter will be can be approximated as a first order. So it will exhibit the behavior of a first order. So this will all come from the modeling. We cannot directly say this is second order, that is third order. So once we model, then we'll know. So the response will be different, but the controller's objective is to make sure the output voltage comes back while the required load current is being supplied.
Okay, and first order is faster, or first order like CMC is a faster response or a slower response?
Again, you cannot directly say. See, current mode control can be also equally made faster. But one thing we can point out is here we have more degrees of freedom. Here we have more degree means 2 degree. Here we have less degrees of freedom. Because if you see in the second order, I can play with the rise time as well as damping. Right? Here I can only play with rise time because there is a step. In the case of first order, it will go something like this. But in the case of second order, I can make sure it will have something like this. So I can play with damping as well as rise time because first order is over damped, right? First order is over damped because you will not see any of this. And second order can be critically damped, under damped, or damped, but usually slightly under damped is preferred, slightly under damped, meaning close to critically damped. So in the case of voltage mode control, I might have more flexibility, but response can be improved in voltage mode control as well as current mode control with both feedback as well as feed forward. So depending upon the application and things, we can choose between voltage mode as well as current mode. And of course, both of them have pros and cons. Now in my upcoming slides, I have put voltage mode and current mode control where I'll be discussing in detail. But Until this point, if you have any questions, you can ask. Any questions, or is your doubt clear?
Yeah, I'm fine, thanks.
So if others have any queries, they can ask, else we can move to our next topic, which will be the voltage mode control as well as current mode control architecture. No queries? Okay. So let us move to our next topic, which is the voltage mode control. So in voltage mode control, there is only single loop voltage loop. So this is also called as single loop control, because it has only one loop, which is the voltage loop. And if we what is the single loop? Voltage. So it is very simple to understand. This is our buck converter or plant. And then we notice sensed, and then here there is a gain. This is a sensing gain. As I have said, the voltage has to be stepped down so that it can be made in the range of, say, digital control of ADC, but 200 volt cannot be directly sent, so it has to be stepped down. So it can be 1 by 100, 1 by 200, depending upon the application. This can be chosen. There is less than a minute, so if this meeting ends, kindly join back. Then we can again continue our discussion. So once this sensing gain is applied to V0, we'll get feedback voltage, which is then subtracted from the reference voltage, and then we'll get error voltage. This is our error voltage passed through a controller. This is our controller. And then we have discussed this in detail. This is the modulation technique. If this meeting ends, kindly join back. Can you see my screen?
Yes.
Yeah. So in the case of voltage mode control, it's a single loop, very simple. So it has, I can say 1, 2, 3, 4 things. First thing is 5 things basically. So let us draw it so that we can identify which is what. So this is our error generation, and this is our controller, and this is our modulation technique, and this is our plant, and this is our sensing circuit. So if I highlight, so we have our error generation block. And then we have our controller block. And then I have shown the modulation technique. Again, it can be leading edge or trailing edge. And then we have the sensing circuitry. I think this color will not be visible. So let me change the color. Sensing circuitry to step down and also to filter. And then we have the plant. So this is the overall architecture of the voltage mode control. Very simple and straightforward. We have one loop because as you can see, this is the only loop. So this is the only loop, right? So this is the only loop. So that's why it is called single loop control. And this single loop is voltage. So that's why it is called voltage mode control. And then we have thoroughly discussed about modulation technique. Error generation is straightforward. Sensing also we have discussed. Buck converter also we have discussed. Controller is something that we have not discussed yet. And we'll discuss in the future how to design controller for voltage mode control. Also how to design the controller for current mode control. So this is the overall architecture of voltage mode control. If you have any questions, you can ask, else we'll move to the other control, which is the current mode control. Any doubts you have? Okay, so now let us move to the current mode control, which is a two loop control. So it will have two loops. One is the voltage, another one is the current. So the voltage is the outer loop and the current is the inner loop. Okay. So as I have mentioned, there are two loops. So first, let me highlight the two loops. One is this. So this is one loop, and then this is the another loop. Okay. So again, let us segregate different things. So this is our plant, and then these are two type of sensing. Sensing is equally applicable for current as well as voltage, right? So voltage needs some stepping down, whereas current has to be converted from current to voltage, because current inductor current is in the current form. Right now we need to sense it, and then it has to be made as a voltage, because we are dealing with voltages whenever we are comparing using a comparator or anything. It is basically a voltage, so that KC will convert current to voltage. So the units will be voltage. So the units will be voltage per ampere. So here it is converting the current into voltage. So in this course, the details of the current sensing are not emphasized, but there is another course of sir where sir has discussed what type of sensing, current sensing are used, and what are high bandwidth current sensing. But that is not part of this course, so that's why I'm not covering that. But if you are interested, you can go through the other course, which is digital control in switch mode power converters and FPGA based prototyping. I think it is in week 5 or week 6, but that is not in this course. But I'm just giving you the information that voltage sensing is different and current sensing is different. Current sensing has more like bottlenecks, because we are basically converting current into voltage. So it is like little bit more challenging compared to voltage sensor. So now this is done. Now again we have our controller. Okay. And then again we have this modulation technique. Again, it can be leading edge, trailing edge. The details, I have considered one problem where I'll be discussing this. So again, this is the plant. And this is the sensing. So as I have discussed, if you have V0 sensing, it is basically stepping down. And also it can have a filter, low pass filter, LPF, low pass filter, so that the noise will be removed. Whereas if you are going to current is basically converting ampere to voltage, because we need in terms of voltage, and usually current sensing has to be of high bandwidth, because it needs to have the ripple current information, right? So here it is more challenging, I would say. Let us not go into details of what type of sensing can be used. It is more challenging compared to the voltage sensing. And now we have again controller. So now this controller is of current mode control. It can be different from this. The same controller, if you plug it here, it may not work. Usually it will not work. So these two may or may not be same, and may or may not work. So these two are different controls. So depending upon the modulation technique, not modulation, depending upon the control technique that we have selected, we have to design the controller accordingly. And this is the modulation technique. Again, it can be leading edge or trailing edge. So just to quickly compare, here we have error generation. Okay, error generation. I think I have missed out. Okay, mention error generation, controller, modulation technique, plant, sensing gain, and one loop. Here, the outer voltage loop, whatever that is coming, that is being compared with the current which is in the inner. If you see here, we have one loop and it is compared with the sawtooth. So now, instead of this sawtooth, we don't have this sawtooth. So just to highlight, here we have sawtooth, right? So instead of sawtooth, we are not comparing with sawtooth. Instead of sawtooth, we are comparing with this current only. So instead of sawtooth, what do we have? We have current. So this is the current waveform, like inductor current, which is like this. So this is the current that we are comparing. Whereas in the previous case, we have this type of sawtooth. So this is in voltage mode control, we have sawtooth, and this is in current mode control. And I have missed out one block diagram, which is this error generation. So I'm using same color so that when you read, go through the notes, you can correlate what is the difference between this control and that control, and you can see what are the additional blocks. Blocks are more or less same, except that we have one additional sensing because here there is voltage, here we have current as well. And here we are comparing with the inductor current because it is current mode control and it is in the inner loop. So now this loop is not there here. Instead of that, we directly have sawtooth. So there is no loop. So if the outer loop remains same and the inner loop is coming from current, this part, this VR part, then it becomes current mode control. So that is the only difference between this and that. Although they may work totally different, that's a different thing. But when we look from the architecture, only this additional thing is coming in current mode control, as the architecture remains the same. So is this clear? Like, am I able to convince you or make you understand the architecture, or are you a little bit confused? If you have any questions, you can ask. We can spend time here and then we can move to the modulation techniques in Kharagpur. Is this clear? Or do you have any doubts in both of any of these control techniques? Clear. Okay. So now this is one MATLAB implementation of current mode control that I have gotten from sir's lectures. So basically, there is no plant here. We are in the feedback. So we'll use the same color so that we can identify which is what. So can you identify what is this block? What is this block? Anyone? Comparative. No, Arun, it is not comparative. So basically, we are subtracting Vref minus V0. So if I go back here, now can you tell me which block corresponds to that I have highlighted?
That blue
Error
part,
generator.
light blue.
Yes, error
Error.
generator. I'm using same color so that there will not be any confusion. And here sir has not used sensing because this is simulation, but sensing gain is needed for practical. For simulation, it works because it is ideal case. Whereas in the case of practical implementation in the hardware, you will need sensing gain. And what about this? This block?
Controller.
Controller. Very good. So it can be PID. The block remains PID. If you put D 0, then there is no derivative. So you can use as KP, KI, KD, but the block name is PID. So that's why it is shown as PID. And then the rest of the part. This entire thing, what is this? Okay, if we go back here, basically what is happening, there is a set pulse, there is a reset pulse coming from a comparator. The input of the comparator is control voltage coming from the controller, and then it is compared with the inductor current. So reset pulse, set pulse is coming externally, reset pulse is coming from the comparator. Comparator one input is the control voltage of the controller, and another input voltage is the inductor current. So this is the trailing edge PWM generation. Very good. So this is trailing edge PWM generation. Now I'll also discuss about what is trailing edge, what is leading edge, how to get the difference. So this is basically PWM generation block. And here it is trailing edge block. And this is the comparator block and inductor current. So this is the control voltage, as you can see, silence highlighted. So this is the control voltage. And then this is the inductor current. So inductor current is compared with the control voltage, and control voltage is coming from the output of the controller. So these two are getting compared. In the case of voltage mode control, instead of this IL, what we'll be having is we'll have a shortage. In the case of voltage mode control. And then everything remains same. So that is the architectural difference. Clear?
Yes.
Okay. So if others have any doubts, they can ask, as we will now discuss about the trailing edge as well as leading edge modulation in current mode control. In the last week, we have discussed about the voltage mode control, which is like this sawtooth, where we have discussed both trailing and leading edge. Now, first we'll see the timing diagram, then we'll move on to the implementation, how we'll implement using set reset pulse. Okay, if you don't have any question, then we'll do trailing edge. Then we will do. So trailing edge modulation is also called as peak current mode control, and this is known as valley current mode control. Okay. So let us quickly draw the diagram. So in the case of trailing edge modulation, so what is trailing? basically when we say trailing edge, leading edge, we are talking about the inductor current. If inductor current is trailing, it is trailing edge. If inductor current is leading, it is leading edge. So let us draw the inductor current. Okay. And we'll also have a peak current, of course. Say this is our peak current, which is basically control voltage. So this is our Vcon, which is then compared with the inductor current, IL. Okay. So if it is peak current mode control, whenever there is a peak, whenever the peak is hitting, then we need to have the reset pulse. So this is our reset pulse. So whenever the peak is hitting, then we should have a reset pulse, like for some time, very minimal. So this is our reset pulse. And where is the set pulse? Set pulse is at the valley point. So this is the valley point. And there we'll get the set pulse. So here there will be a set pulse. And here similarly here there is a set pulse. And here there is a set pulse. This is the set pulse. Now if we are drawing Q, gate pulse. So you know that whenever it is setting, it will turn on, and whenever there is reset, it will reset. So if you draw QG, we'll get QG something like this. So the inductor current is trailing. So the control voltage will become peak. So that's why it is called peak current mode control. If the inductor current is leading, then the control voltage will be at the valley. So then it will be called valley current mode control. So is this clear?
Yes.
Okay. So now I'll use the same figure so that we can correlate easily. Okay. So now there will be slight changes, of course. The control voltage will be at the value because it is value. So now Vcon is at the value. Vcon. Okay. So also now in this case, whenever Vcon hits, then we'll have set, not reset. So basically what happens is set and reset will get interchanged. So okay. So now whenever these two are colliding with each other or whenever they are hitting each other, then we'll have reset pulse. So the reset pulse is now shifted. So then we'll have set pulse, sorry. So now the set pulse. So whenever they're hitting, then they will set. Previously it is reset. So now it will set. So the comparator output is basically setting. And at the peak of the inductor, we'll have reset. So QG remains same. So if you remember, even in the trailing edge, leading edge of voltage mode control, the duty ratio remains same. Only the modulation technique is different. So here also, like set and reset are interchanged, but the gate pulse will remain same. Here, whenever it is hitting the peak, there it is resetting. Here, whenever it is hitting the valley, there it is setting. And here, whenever there is valley, their set pulse is generated. Here, whenever there is peak, their reset pulse is generated. So is this clear? I have kept both side by side so that you can correlate. Because the control voltage here is at the peak, it is called peak current mode control. Here it is at the valley, so that's why it is called valley current. Clear?
Yes, clear.
Okay. So now let us quickly solve one problem, but before that I will. So the problem is draw the control architecture diagram of trailing edge, leading edge. When I say control architecture diagram, I mean this type of diagram or this type of comparator, reset, set, flip-flop, everything. So let us first paste this here. Okay, so if we draw trailing edge, so the point is very simple. First, we have to write the comparator, and then we have flip-flop. So first, let us start from the comparator. So let us start from the comparator. So comparator, always one input is IL and one input is VCon, right? So one input is IL, one input is VCon. So now in the case of trailing edge, it is generating the reset pulse, right? Comparator output is reset pulse. So the comparator output is reset pulse to the SR flip-flop. And then it's a reset, so it also has a set pulse. So this is reset. And this is set. And set pulse is what? It's a fixed frequency switching clock. And then output Q. This is R, S, and this is Q. So this is how we'll draw. So now can any one of you tell whether IL will be positive or VCon will be positive for the comparator? Because whenever IL is crossing VCon, whenever IL is going above VCon, then we are getting reset pulse, right? So whenever IL is above VCon, then reset is high. So whether IL will be positive or VCon will be positive.
IL.
IL, very good. So IL will be plus and VCon is minus. So here for the picture, like understanding, I have drawn like this, that it is not crossing. If you implement it practically, you will have the inductor current like this. And maybe let me use the same color. So practically how you will get is, you will get inductor current like this. And then control voltage slightly lower. So you will get reset pulse of certain value. So very less, but you will get reset pulse. But here I have shown ideal case where it is just touching. But when you implement practically, there will be some gap because then only the pulse will be detected, right? So this is how the circuit is there. So now let us use the same figure here. So now what will be the changes here, anyone? So first of all, output of the comparator is set pulse or reset pulse?
Set.
Set.
Set. So that is the first change that we have to do. This is set and then this is reset, right? So let us also interchange this. So this is our set, this is our reset. Now if I have, this is our set pulse, this is our reset pulse. Okay. So any other changes will be there?
Polarity of the comparator.
Yes. So if you see, when is the set pulse generated? When IL is going below VCon. So IL has to be minus, VCon has to be plus. So IL has to be minus, VCon has to be plus. So this is the change. So when we are talking about trailing edge modulation, as well as when we are talking about leading edge modulation, the changes will be in the flip-flop as well as the comparator inputs, and the comparator output is set in one and reset in other. And also trailing edge means inductor current is trailing. So inductor current is trailing means it is below the VCon, or I can say VCon is the peak. So that's why it is peak current of control. In the case of leading edge, inductor current is leading or inductor current is above the VCon, which means VCon is at the valley point. So that's why it is called valley current of control. So this is the modulation technique. Again, this is for fixed frequency, so that is very important. What happens if it is variable frequency? That is next week's topic. So that we'll check in the next week. So this week is fixed frequency control techniques. So the frequency is fixed and the duty ratio is changing, on time is changing. But in the next week, we will discuss about constant on time, off time, where on time or off time is fixed and the time period is varying. So the fixed frequency will become fixed on time or as well as fixed off time. So that is next week's topic, but I'm just trying to explain now so that you can understand the difference. So is this discussion clear? Understanding the timing diagram as well as the architecture, how it looks like. So this is what you exactly implement in the MATLAB. So if you have any questions, you can ask me. Else I'll just quickly summarize what we have discussed today. Any queries?
Teja, just for practice purposes, will it be
Yes.
possible to get the Simulink files that sir was showcasing in the
Sorry,
classes?
can you repeat?
The Simulink files that sir is showing in the classes, will it be possible to get some of those files just for practice purposes?
Okay. Okay. Actually, I don't have access to those files. So like I work under him only. So I can ask him. Also, you can put a question in the forum. So I'll also talk to the corresponding TA whether it can be accessed or not. But like as our supervisor says, it is required for the students to do by themselves because I'll tell you what happens. So say you got the Simulink model, you will just run it, you will not try to understand it. But once you start making the model, you will make a lot of mistakes and then you will try to debug it. So in that process, you will learn more about this blocks and everything. Even at the early stage of my PhD, I have started doing it by myself and it doesn't work. So then I have to debug like why it is not working. I'll go block by block and then I'll check block by block. So then I'll find my mistake. Then I'll learn something in the process of debugging. So same happens everywhere. So you can try by yourself. If you get stuck, we are there to help. But you can also ask in the forum whether they can share or not. But I highly doubt that they'll share because learning is a process. And if you do it by yourself, you will make mistakes because uh, like no one can get the model right in the first stage. Then we are not learning anything. So we'll make mistakes. And then when we debug, then we'll know like where we are making mistake and we'll understand.
Okay, thank you.
Okay, so Naveen has asked one question: why practically IL crosses VCon? IL should cut off before VCon, sir. So basically, practically what happens is IL will slightly cross VCon because we need to have reset pulse. And then once this reset pulse is coming, then the flip-flop will turn off. So the moment it touches VCon, to the moment the QG turns off, also the QG falling does not mean the switch will turn off. From the gate pulse to the switch, there again there is some delay TD. So that's why there is certain region during which the inductor current is still rising. Ideally, in the simulation, if you see, it will just touch it and then it will turn off. But practically, it will turn on for certain time because like the moment the reset pulse is generated to the moment gate pulse is turned off to the moment switch is turned off, there is some delay. So this delay will be reflected as the some rise time or some on time of the switch. So this is the practical waveform. This is the simulation or the ideal wave. This you can see if you incorporate some delay in the MATLAB block, but you have to deliberately incorporate the delay, whereas it inherently exists in the hardware. So you will see this hardware in the hardware and you cannot remove this delay because that exists because of the this flip-flop as well as gate driver circuit, other circuit. Whereas in the case of Simulink, you don't have all the circuitry. So you can add delay to see this effect, but again, that is not relevant as of now. This is something that you will see in the hardware. So if you don't have any questions, I'll quickly summarize. So this week is about fixed frequency control techniques. But before we went there, we have discussed certain important things like practical voltage source, where we have considered three cases. Where first case we have considered the ideal voltage source, where the voltage is constant. In the second case, we have considered ideal voltage source with parasitic resistance, where the voltage will linearly fall. In the third case, we have also incorporated frequency dependent parasitics, and we have seen because of this frequency dependent parasitics, there can be some additional harmonics, basically the second order dynamics because of this LNC. And because of this harmonics, there can be EMI issue if we are taking pulsating current at higher frequency, then these harmonics can cause EMI issues. And then we have also solved one problem where we have discussed about the MATLAB implementation of this practical voltage source, which Sir has also explained, but again, we have discussed in detail because we have to use one bias blocks. For capacitor, it is easy. For inductor, it has to be slightly modified. And we have seen that always we have to convert everything in one bias blocks, and then we have to implement, and then we have combined the inductor dynamics as well as capacitor dynamics to get the overall dynamics. Then we have moved on to the objectives of the overall system. We have discussed about four objectives, which are static, dynamic, operating requirements, as well as fault management and protection, and what comes under these objectives and why they are important. And we have also correlated. Sometimes we have taken examples of mobile phone and laptop, and we have correlated so that we can get better understanding. And we have also discussed about the overall system and what are the blocks like plant, sensing circuitry, feedback, feed forward controls, as well as modulation techniques. So irrespective of the control technique, these blocks are there. Only the architecture inside the block might change, but the blocks will be there in the overall control systems. And then we have moved to the actual use of input voltage feed forward. In the case of buck converter, it is straightforward, and the output voltage will become independent of the input voltage, and irrespective of the input voltage, output voltage will be fixed and it is independent. Whereas the same logic can be applied for other converters, but it may not work according to the way we are expecting because there can be nonlinear dependency between the output and input voltage. So there, the logic has to be changed, and it can be challenging and may not be as simple as buck converter. But still, input voltage feed forward can be applied, but it might be a little bit complicated and practically very challenging. And we have seen that in such cases how the output and input voltage are related. And someone has asked doubt on voltage mode control if there is any load change. So I have also explained, and these details of the model and everything we'll discuss in detail in the upcoming weeks, where we'll be discussing about voltage mode control model, current mode control model. And then we have discussed about the voltage mode control architecture, where it consists of error generator, controller, the modulation technique, and then the plant, and then the sensing it. All are in a loop, single loop, which is a voltage. So it is called voltage mode control or single loop control. Then we move to current mode control, where it has two voltages, two loops, one with the voltage, one with the current, but it also has a plant, sensing circuitry, error generator, controller, as well as the modulation technique. Here sensing are two different sensing. One is voltage sensing, one is current sensing. So sensing is not part of this topic, not part of this course. So that's why we didn't go in detail, but you can always explore in other courses as well as on NPTEL. Then we have seen the MATLAB implementation of the current mode control architecture, and we have correlated between the architecture as well as this. So I have used the same color so that you can correlate between this diagram and that diagram. And then trailing edge and leading edge modulation of voltage mode control are already discussed in the past week. So in this week, we have discussed about the current mode control, which are also called as peak current mode control as well as value current mode control, because the control voltage is peak in this case and value in this case. And we have seen how set pulse and reset pulses are generated, and then how they are used to generate the gate pulse. And then we have also seen the implementation using the comparator as well as SR flip-flop, and then how they are different for this as well as this. So the only difference are set and reset pulses and the comparator inputs. So this is all we have discussed in this week. If you have any questions, you can ask, else we can wind this session and then we can meet in the next week. Any queries you have?
No, thank you, Teja.
So if you don't have any queries, then we can wind this session here. I wish you all the best for your assignment 3. So once you follow the lectures and understand the concept, it will be easy, and you can do well. And yeah, let's meet again in the next week with week 4 content, which is variable frequency modulation techniques. So we'll have more discussion, and we'll solve a couple of problems in the next week. So see you then. I wish you all the best, and good night. Thank you for joining. It's a nice session. Thank you, Suganya, and thank you,
Thank-
Manu. Thank you, everyone.
Thank you, sir. Good night.
Thank you. Good night.